My name is Binggeli, and I'm the lecturer of this course, Electrons and Phonons in Solids. So this is the title of this course, Electrons and Phonons in Solids. So we call it the EPS course internally, and so this is my first name, Nadia Binggeli, and you can find me in the Leonardo building, room 299. So I will be lecturing this course. And together with Natasha Stojic, she is also at ICTP, and she will give lectures later on and also the tutorial. So this is me, and my colleague is Natasha Stojic. And she will meet her later on during this semester. So the semester the course will include 24 lectures, about 24 lectures. And there will be a midterm test and a final exam. So the midterm will count just a fraction, a small fraction in the final score. It is mainly to give you an idea where you stand and how much, if you see there is a problem, how much more you need to work to make it for the final exam. So the final exam will include two parts. The first part will be 20 questions with multiple choice answers. And the second part will have two problems of which you have to choose and solve one. Only one will be graded. So this is the form of the exam. And in the first part, we want you to have understood the concepts presented in the course, and in the second part to use them to solve practice some new problem. So this course, one thing, during the course, please interrupt me. If there is something you didn't understand, it's better to fix it early, not just before the exam, if there is something that you feel you don't understand. So this course will be in the independent electron framework. Or in the independent electron approximation. By contrast to what you will see in the second semester with the many-body course. By independent electron approximation, we just mean that we will solve typically a one-electron Schrödinger equation in a Mill field. So this is what I mean by independent electron approximation. And as textbook, as support textbook, we suggest Ashcroft and Merling. solid state physics book. So there are some copies in the library in the Diploma section. However, all what you need to know for the exam will be in the course. So this is just as additional material if you want to understand better or differently, having seen presented the same concept in a different way. We give you also this reference as support, but as I mentioned, everything you need to know is in the course. Everything you need to know for the exam is in the course. All right, so now I would like to ask you a question. It's just to know, yes?
Maybe I missed something. You are saying everything we need in the exam is in the course, as in the lectures, or?
In the lectures, in the course that we will give in the lectures, yes. So just since you are coming from different backgrounds, different countries, I would like just to know who of you know what is the Bloch theorem. I'm not asking you to tell me what it is, just for me to know how many of you know already what is the Bloch theorem. We will see it in the course, so for some parts will be a repetition, but just to have an idea of what is the percentage of you who have already seen the Bloch theorem. Can you raise your hand? Those who already know the Bloch theorem, what it is. Bloch theorem? You, one. Okay. All right, so that's good. Most of you will see the Bloch theorem for the first time in the course. This is the central theorem in what we will present, and we will use this theorem heavily in this course. So what you need instead to know for this course, which I assume you have already seen, is the hydrogen atoms, so the eigenstates of the hydrogen atom, the sp states and so on, the spherical harmonics. So this you must have seen, and if you feel you are not sure about it, please look again at your quantum mechanics course and be sure you have in mind the hydrogen atoms and its eigenstate. And the second item that I assume you have seen is perturbation theory in quantum mechanics. So this chapter I assume you have seen, and please, if you I'm not sure you remember, please go to your textbook in quantum mechanics and have a look to be sure you know that for the course. So this is what I will assume you already have seen. Okay, so now let me start with the outline of the course. So, okay, so outline. This course, EPS. So the first part will be on the crystal structures. And there, the basic concepts that we will see are the Bravais lattices, or the Bravais lattice. And we will see also then what is the reciprocal lattice. And also the Brillouin zone. So this is the first part of the course, which will be on the crystal structure, the general properties of crystal structures. Then we will move to the properties of electrons in an extended periodic system. So the second part will be on the electronic state. Electronic state in crystal. So the general properties. Of the electronic state in crystal, in periodic, extended periodic systems. So we will first see the Bloch theorem. So this is a fundamental theorem in solid state physics. And then we will see the concept of band structure, what are band structures. Electrons in crystals. And then we will see some methods to calculate band structures. So, methods or models for band structure calculation. And the first one will be the plane wave method. The plane wave method. So free or quasi-free electron model. And the second method will be the tight binding approximation. So these are the methods or models that we will see to calculate band structures. So this is for the second part. And the third part of the course will be on applications of band theory. And the first application you will see will be on transport. Electronic transport in crystals. And the second one will be on the optical properties of crystals. All right. Now the next part will be the Born-Oppenheimer approximation. This approximation is the link between the electronic problem and the problem of the ions or nuclei in crystal, that is the structural properties of the crystal and the also it's the equilibrium structure of the crystal and the lattice properties. Also phonons will derive from the Born-Oppenheimer approximation. So this approximations makes it possible to, starting from the solution of the electronic problem, to obtain the energy potential for the ion, to determine their ion or nuclei, to determine their equilibrium property, vibrational properties, and so on. So this is the Born-Oppenheimer approximation, which gives access to the crystal structure properties. Structural. It is to determine the equilibrium properties of the nuclei in a crystal and the crystallographic equilibrium properties. So crystal structural properties, it gives us access also to the phonons, to the vibrational properties of the crystal, phonons, and it can be used also, it's the basis to carry out molecular dynamic simulations of the nuclei in condensed matter. So it gives access to also molecular dynamics. Or those want to perform molecular dynamic simulations at final temperature of the properties of the nuclei in a crystal. So this is another part of the course, and the last part will be on phonons. The last part of this course will be on phonons. Okay, so this is the outline of this course. Now, before starting the part of the crystal structure, I would like to ask you a question. In this room, can you see or identify any single crystal? So, a piece that is a single crystal. Is it common? Can you identify any single crystal in this room?
Maybe that was uses quartz crystal.
Yeah, that's one thing. Yes, quartz crystals. So we found one. Any other?
Did you have on your name?
Yeah,
Oh.
the gems. Yeah, yes. And so some gems and the silicon of the transistor in devices, electronic devices, computers. So more or less we are there. So most of the materials are not single crystals. Most of the materials are either composites made with two or more different materials, or polycrystals. So, for instance, typical metals, the aluminum here, or gold, or most metals are, all metals that we see in practice are polycrystals. That is, if one looks with a microscope at the metals, one will see some little grains. So, most materials are polycrystalline. Polycrystalline, composite, different components like concrete, or amorphous material like glasses. Anything but single crystals. So, for instance, if one looks at a piece of metal with a microscope, this is the microscope, one will see some domains with little grains. Something like that. And so on. Well, you can. Okay, so you will see with a microscope, looking at a piece of metal, something like this, and these are grains. So this is a grain, and the typical size are 1 to 100 micrometer. So these are microcrystals. These grains are just microcrystals. So this is a polycrystalline material, and it's composed of grains with domain walls between the grains. So Knowing that, why in this solid state physics course do we study, because you saw the outline, single crystals, the properties of crystal, what makes it reasonable, and why are we doing that, knowing that actually most material are not single crystal, and of course we would like to predict or to study materials properties in the end used in practice. So who can answer this? Why do we study single crystals in this course?
I think because they found the basis such that we can create a mathematical standard based on them, and then we can elaborate on other crystals.
Okay, this is part of the answer. That is, we need some models starting from simpler cases that are relevant, and then we can go further. But there is still something missing. That is, if studying single crystals here would give something totally different from the final property, there would be a problem. It would be useless. So, what is missing? What saves the simple model in this case of studying infinite crystals to predict the properties of material? There is something missing still. That is so that it's sound, that it makes sense it's not enough. What is the reason that the reason it works or it makes sense is that many of the material properties are actually established on a very local scale. So basically, many properties are already established at for a piece of matter that is of the order of of the nanoscale, a few nanometers, or even smaller in some cases a bit larger. But basically, many properties, including whether it's an insulator or a metal, are established on a very local, small scale. And this is the reason that it makes sense to start from there. So, starting, one can already obtain reasonable, a good description of the properties on a local scale, and then starting from there, having this property for the crystal, one can include perturbatively other properties like the effect of domain walls, having studied the properties of the infinite crystal that also corresponds to the properties inside the microcrystals, where the property don't depend much on the boundary condition, in particular the band gap. One can then include perturbatively other properties like the effect of the domain walls. It will introduce, for instance, some levels in the gap or change somewhat the properties. So this is the reason. For instance, it's not only true that it's the properties many properties are established on a local case, scale, actually some property don't depend much on the long-range order. This is, for instance, the difference between a crystalline material and an amorphous material. For instance, glasses or SiO2, let's say, crystallizes in the quartz structure, but it can also be amorphous if one cools it from the melt very quickly, well, not too slowly, one will obtain an amorphous material. So they are crystalline forms and they are amorphous forms, but in both forms of silica, SiO2, the local environment is the same. That is, the silicon is surrounded by 4 oxygen that forms a tetrahedron. So in the silica and in quartz, one has the silicon that is surrounded by 4 oxygen, and they form a tetrahedral. These oxygen form a tetrahedral unit. The same in the amorphous and in the crystal. When the oxygen are bound to another tetrahedral, silicon-centered tetrahedral unit, and in the crystal this angle is fixed, and there is a long-range periodic order, whereas in the amorphous material one keeps this network, but the long-range order is not present. And in both materials, the gap is about the same. It's between 8 and 9 eV, and it's established already by the local units, the tetrahedral units. So also in this case, the band gap doesn't really depend much on the long-range order, whether it's amorphous or it's crystalline. Has not a large impact on the band gap, has a very small impact on the band gap. So this is also another example that illustrates this usefulness of the crystal as the starting model. Okay. All right, so having said that, now we can start the part on the crystal structures. So an important concept in crystal structure is the Bravais lattice. So the Bravais lattice is defined by the set of points R that are indicated by the vectors R, such that R is equal to N1 A1 plus N2 A2 plus N3 A3, where N1, N2, and N3 are integers. And A1, A2, and A3 are linearly independent vectors. So A1, A2, and A3 are linearly independent vectors, and they are called the primitive vectors of the Bravais lattice. So A1, A2, and A3 are called primitive vectors of the Bravais lattice, or generating vectors of the Bravais lattice. So this is in 3 dimensions for a 3-dimensional crystal. Of course, in 2 dimensions, one would have just 2 vectors that are not parallel, and also streamers. It can be extended easily to 2 and 1 dimension, the concept of crystals. So this is the definition of the Bravais lattice with N1, N2, and N3 integers, and A1, A2, and A3, 3 vectors that are linearly independent. So just before continuing on Bravais lattices, I want just to mention the link with crystal structure. So a crystal structure is a Bravais lattice with a group of atoms attached to every point of the lattice, of the Bravais lattice. So this is just to give you the link between Bravais lattice and crystal structure. One also says that the crystal structure is a Bravais lattice plus a basis. A basis of atoms, group of atoms. So I will come back to the crystal a little bit later on today, and now I'm continuing on the Bravais lattice, but I just wanted to mention the connection with the crystal here. Okay, so I will give you now some example of Bravais lattice, draw some Bravais lattice, and it's easier in 2 dimensions, so I will start with the 2-dimensional case. Okay, so in two dimension example of Bravais lattice. So in two dimension, I just need two vectors that are not parallel, A1 and A2, as primitive vectors. So this is A1, and this is A2. So I have two vectors. And now with the definition, I can construct the points of the Bravais lattice with n1, a1, and plus n2, a2. So this is 0, a1, 0, a2, 1 times a1, 0 times a2, 1 times a2, 0 times a1, and I have sum. I have this point, which is a1 plus a2, and I can continue like this. So this is 2 times a1, this is 2 times a1 plus a2, when I continue with 2 times a2, 2 times a1, 2 times a2, and so on. This is minus a1, this is minus a1 plus a2, and so on. And this is my Bravais lattice. So minus a2 plus a1, minus a2 minus a1, and so on. And I can continue over the full blackboard. This is my two-dimensional Bravais lattice. So if I put the n1, n2, I have here 1 times a1, 0 times a2, 0 times a2, 1 times a1, 1 times a1, 1 times a2, 2 times a1, 0 times a2, and so on. So this is the way Bravais lattice looks in two dimensions. Okay. So this is quite general Bravais lattice in two dimensions. Now I can draw some more symmetric Bravais lattice in two dimensions. And a typical Bravais lattice in two dimensions is the square Bravais lattice. So the square Bravais lattice in this case has the two vectors a1 and a2, which have the same norm. So the vectors have a length a, and these vectors are orthogonal. It is ai times aj is equal to delta ij times a square. So I'm just saying that the two vectors a1 and a2 have the same length and are perpendicular. So this primitive vector defines the square Bravais lattice. So I have a1 here, and A2 that has the same length and is perpendicular. And the square Bravais lattice has the points like this. Okay. So this is the square Bravais lattice, and so on. So in the square Bravais lattice, I have my points of the Bravais lattice R, given by R is equal to N1 E1 plus N2 E2 with N1 N2 integers and these two primitive vectors E1 and E2. Now, if I do a change and I consider as primitive vector still A1 here, but for A2, if I consider this vector here, so this would be my A2 prime. So if I consider the points R prime that are given by R prime is equal to N1 A1 plus N2 A2 prime, what do I obtain? So I obtain a Bravais lattice, but what can you say about this Bravais lattice? So I consider as primitive vector A1 and A2 prime.
It's a different way of representing the same thing, like it's nothing different. It's
So
equivalent, those two representations.
Okay, so I obtain the same Bravais lattice. Yeah. So indeed, if I use this as primitive vector, I obtain exactly the same point, exactly the same Bravais lattice. You will agree on that? You see it? No? Yes? Okay, for everybody? So if I construct the point R prime with this, I will map the same Bravais lattice. I will generate the same points. So this gives exactly the same set of points. Then these are two different sets of primitive vectors that give exactly the same Bravais lattice. And actually, I could find an infinite number of sets of primitive vectors that would generate the same Bravais lattice. For instance, if I take as A2 second prime this vector, I would also generate with A1 the same Bravais lattice. So it's clear that I have an infinite number of possibility to generate the Bravais lattice, an infinite set of primitive vectors to generate the same Bravais lattice. Okay? You see that? So, there is no unique choice, and there is actually an infinite number of possibilities. So there exists an infinite choice of primitive vectors that generate a given Bravais lattice. So, no unique choice of primitive vectors for a Bravais lattice. But, of course, there is a simpler, a simple choice, that is these two vectors, A1 and A2, that have the same length and are perpendicular, are the conventional primitive vector that are used to define the square Bravais lattice. There is a simpler choice, conventional choice, but there is no unique choice. Okay? All right. Now, let me draw some lattice. A very popular lattice, which is called the Honeycomb lattice. So the Honeycomb lattice looks like that. It's based on hexagons. These are the points of this lattice. Okay, so, and one can continue up to infinity. So this is the honeycomb lattice formed by these hexagons. So, is it a Bravais lattice or not? Who votes for a Bravais lattice? Who votes for not a Bravais lattice? So, can you generate with some primitive vectors A1 and A2 the full sets of points?
You can, but you need to have two atoms in a basis.
Okay, so the question is, with two vectors A1 and A2, can you generate just with the two vectors A1 and A2 all points? No?
No.
Okay, you're right. You cannot. So this is not a Bravais lattice. Actually, to prove, so this is not. To prove that it's not a Bravais lattice, one can assume first that it is a Bravais lattice and show that there is a contradiction. So if I assume that this is a Bravais lattice, I know that the difference between 2 points of the Bravais lattice must be a Bravais vector from the Bravais lattice. So the difference between these 2 points, the vector D here, must be a vector from the Bravais lattice, if this is a Bravais lattice, and the same for the difference between these 2 points. So D prime here must be a vector of the Bravais lattice, okay? If I assume this is a Bravais lattice, the difference between 2 points of the Bravais lattice must be a vector of the Bravais lattice. So D1 and D2 should be vector of the Bravais lattice. But then, if these two vectors are vectors of the Bravais lattice, also their sums should be a vector of the Bravais lattice. And D plus D prime gives a point here that is not part of the Bravais lattice. So it's a contradiction, and therefore this is not a Bravais lattice. So, just to summarize, in a Bravais lattice, if this vector D and D prime are lattice vectors, because there are differences between 2 points of the lattice. If these two vectors are lattice vectors, then their sum also must be a lattice vector. And here D plus D prime is not a lattice vector. So the honeycomb lattice is not a Bravais lattice. Okay, so the honeycomb lattice is not a Bravais lattice. However, the honeycomb lattice is a crystal structure. So the honeycomb lattice is a lattice with a basis. It is a crystal structure. So in 2 dimension, the positions of the atom in a lattice with a basis is given by the following. So positions So in 2D, the position of the atoms in a lattice with basis are given by the point RE, such that RE, F is for atom, is equal to N1A1 plus N2A2. So this is the part coming from the Bravais lattice, plus a vector di, where the set of di is finite and goes from I equal 1 to n, and these are the labels of the atoms in the basis. Label the atoms of the basis. So basically I have the first part that generates a Bravais lattice, and attached to each point of the Bravais lattice I have this vector di that bring to the atom close to the points. So a set of atoms attached to each point of the Bravais lattice. And this is repeated periodically with the periodicity of the Bravais lattice. So this is how I define the crystal.
Can one atom be shared by 2 Bravais lattice points?
Excuse me?
Can one atom be shared by 2 Bravais lattice points?
No. No. This is the smallest set that would fully describe my crystal. So you have just the minimal.
Here, like the
Yeah.
capital N is not unique. Is it, or is it unique? Capital N. For example, the number of atoms that can be attached to a Bravais lattice point. Can we have like 2 atoms attached to a Bravais lattice point and 3 atoms attached to a Bravais lattice point and create the same crystal
Okay,
structure?
so you have a given Bravais lattice, and then from that you have well, okay. No, you have some choice in the I modulo a Bravais lattice vector. This is your freedom, but the number for a given Bravais lattice is fixed. It's the smallest numbers that allows you to describe the full crystal given the choice of Bravais lattice that you have.
Given the choice of Bravais lattice, but
Yes.
we can
Yeah.
have different choice of
Yes.
gravel lattice, and then maybe n will be different number
Okay.
of atoms attached to.
Yes,
that
it's
one.
always possible to increase. So if you have a Brave, I mean, you can always have a superstructure. That is, for instance, you can decide to double the number of atoms in the cell, and you use a larger
Different
A2.
gravel lattice.
So that's possible, yeah. But, okay. This n, once you have fixed your Brave lattice completely, you have an n
Unique choice.
which is unique, yes. Okay, so the honeycomb lattice is a lattice with a basis. So now, since I have drawn here the honeycomb lattice, I can define my A1 and A2 vectors. So I will choose, for instance, this as A1 and this as A2. So this would be my primitive vectors, A1 and A2. And then the vectors D1 and D2 would be, okay, so I have the A1 and A2, and this, the honeycomb lattice can be obtained with these two vectors with as n, small as n equal to 2. So there are 2 atoms in the basis. And these 2 atoms would be given by these 2 vectors. D1 is equal to 0, 0. So the first set of atoms would be, one would be sitting here, and then all the images that can be obtained with N1, A1 and N2, A2 would bring to this point here, the big points in white. So I obtain this point, this point, this point. I would obtain also this point with minus A2. I would obtain also this point with with minus 2 times. Oops. No, I mistake. This one is not obtainable from there. So I would obtain this one. And I would obtain this one and this one, for instance. And I would obtain also this one. So with this D1 and N1, A1 plus N2, A2, I would obtain all the points, the big disk here as lattice points. And now if I consider for D2, the second vector in my basis, the vector here D. Then I would obtain this point, of course, and then with all the images that I can get from there, that is this point. If I subtract A1, this point, if I subtract it again, with adding A2, I would obtain this point. Subtracting then A1, I would obtain this point. And if I subtract again, I will obtain this point. And starting from there, if I subtract A2, I would obtain this point. And if I subtract A1, I would obtain this point. So with this second vector here, I would obtain all the points in red, and the first vector was giving me all the points in white. So with this basis, D1 and D2, and this primitive vector A1 and A2, I obtain the full set of points of my honeycomb lattice. So it's a crystal with a basis of 2 atoms. So this shows that the honeycomb lattice is a lattice with a basis. Okay? Everybody agrees with that? That is the crystal structure given this definition? All right. Okay, so now we have seen in 2 dimensions a crystal structure. Can I erase it, or you are still doing? Okay. Is okay? I can erase this part. So just a question now for you. If I draw a square lattice, and at the center of each square I add a point. So I'm getting this. Is it a Bravais lattice or a crystal? I mean, is it a Bravais lattice or not? All Bravais lattices are crystal structure, but not all crystal structure are Bravais lattices. So my question is this a Bravais lattice or not? Who says yes?
Actually, if we look from this part, it's just a parallelogram. So
actually, it's a square.
no, like we can create a A1 as
okay,
A1.
it's because I didn't draw it well, but Okay, these are square.
Okay, actually it can also be a square, smaller
It's
square.
square, yeah, yeah. So actually it is a Bravais lattice because I can find a set of vectors, linearly independent vectors A1 and A2 that generate the full lattice, so it's a Bravais lattice. And in addition, it's a square Bravais lattice, because if I had drawn this better, you would see that these two vectors have the same length and are perpendicular. So it is a Bravais lattice, and in addition, it's the square Bravais lattice, or a square Bravais lattice. So the answer is, it is a Bravais lattice, and it can be described also as a crystal structure with more than one atom in the basis, because, of course, if I start from the square lattice, I can also describe this set of points as a crystal structure with as primitive vector, this vector A1 and A2, and with two atoms in the basis, this one, for instance, and this one. And from there, I generate the full set of points. So I can also view it in a more, it's not, in a different way as a crystal structure with two atoms in the basis. It's always possible to find a crystal structure with a larger, with more complicated or larger length of vectors and a larger number of atoms in the basis. One can always describe it as a bigger system with more atoms in the basis and a crystal structure of this type. The Bravais lattice is something special in the sense that it has as number of atoms in the basis just one. And just one. And I mean, a Bravais lattice is a crystal structure with n equals 1 here, just one atom, or 1 point.
Excuse me,
Yes.
you call this like a square Bravais lattice, but we can also like create this thing and like generate all the points. So it can, like, why call it a square Bravais lattice? Because there can be multiple different ways to generate the points. So
Yes, but as I said, a crystal structure, a Bravais lattice is always a crystal structure, but a crystal structure is not necessarily a Bravais lattice. It's more, Bravais lattice is something more
basic.
unique, basic, yes.
But given a like this, normally look like directly looks like a square thing. Like even if like we remove that central points, like it's a it's a Bravais lattice, like a square Bravais lattice. But we can also have another set of like primitive vectors which are not perpendicular to each other. So like why should we call it just square Bravais lattice? It looks square, but there are other possibilities.
Because there are only few Bravais lattices. So it's nice to have just a few of them because it maps all crystal structures.
So we're trying to find the minimal.
Yes, we we are starting from the simplest units. And Bravais lattice is something that is common to all crystals, and there are just a few of them. So we will come to that.
So should I conclude that if, for example, one of the atoms was missing, then we could say it's not a square lattice, because the square thing, the square,
Just one atom missing.
if there is
in-
one missing in that, for example, this one at the corner, then probably the square should.
But
come
you
into-
mean missing here, and then you keep all the other
Yes,
parts,
yes,
the
yes, yes,
defect?
yes.
Well,
Ev-
then it's not a crystal,
everything
or
is
it's a crystal with
Then
a
it's not a square
defect.
lattice.
I mean, a crystal needs infinite periodicity, and that's why we have this Bravais lattice, because here N1 and N2 are all possible integers. So the Bravais lattice is, I mean, this is the part that gives you the periodicity, the infinite extension, extended system. Of course, I'm drawing it only in a reduced part of the blackboard, but we are talking about crystal, and if you have an atom missing, you have a defect in the crystal, but it lost the periodicity. Yeah, the crystal implies the periodicity, which is given by this part. N1 and N2, which go to, can be any integers and go up to infinity. Okay, so let me just start and I finish next time, since you asked about the Bravais lattice, and I mentioned that there are just a few of them. So I wanted to tell you about these Bravais lattices in 3 dimensions. Okay, let me start. And so, example of 3, this time we go to 3D, Bravais lattices. So the simplest in 3 dimensions is the cubic lattice. And the cubic lattice is defined by taking 3 primitive vectors, A1, A2 and A3, that have the same length. That is A, and that are all perpendicular. So AI times AJ is equal to delta IJ A squared. So the most symmetric Bravais lattice in 3 dimensions is the cubic Bravais lattice. So I have a vector A1, the vector A2 in the plane here, I mean, the base is perpendicular to A1, so I show it this way. So A2 is perpendicular to A1 and has the same length than A1, and A3 is perpendicular to A2 and A1. So it's perpendicular to A2 and it's perpendicular to A1. So the 3 vectors are literally perpendicular and of the same length, and this generates the cubic lattice. And so this is the most symmetric lattice, one of the most, well, in 3 dimensions. If I reduce a bit the symmetry, I have the tetragonal lattice. And the tetragonal lattice has A1, equal to A2, or can be defined with primitive vectors such that A1 has the same length than A2, but the length is different from that of A3. And all angles are 90 degrees. So I have my vector A1 that is perpendicular to the vector A2, and A2 has the same length than A1. So these vectors are perpendicular and have the same length. A3 is perpendicular to A1 and to A2, but has a different length. So it's perpendicular to A1 and it's perpendicular to A2, but it has a different length. So this is called a tetragonal parallax. This is the tetragonal parallax. And then, lowering even further the symmetry, I have the orthorhombic. Lattice. So in this case, one has A1 that has a different length than A2, that has a different length than A3, but all the angles are 90 degrees. So 3 vectors with different length, but all primitive vectors A1, A2, and A3 are perpendicular, and with that one generates the orthorhombic lattice. Okay, so I guess I will stop here. I will tell you about the other type of Bravais lattice in 3 dimension tomorrow. So if you have questions, feel free to ask. It's a good time. All clear? Okay. All right. So let's stop here.